I'm Mauritius Bell, and this is what's in my bag, or my bag. I'm the Senior Manager of Dive Operations and the Diving Safety Officer here at the California Academy of Sciences. My team's responsible for the safety of diving conducted here in the Steinhardt Aquarium, but also in the field. We train divers to engage in diving at all levels. We're also responsible for all the equipment. We also serve as support personnel and in-water personnel, particularly for our deep mesophotic dives. I have a couple items here to show you. This is a sampling of the equipment that we would use on like an expedition like the one we just mounted to Guam a couple weeks ago. First item we have is a closed circuit rebreather. So a rebreather is a form of scuba, self-contained underwater breathing apparatus, except for it's a closed circuit form of scuba. It's very efficient in that when we exhale, the gas stays in this breathing loop. What you see is a mouthpiece very similar to an open circuit scuba mouthpiece, but when we exhale, the gas goes through a one-way valve and into this hose and into what we call a counter lung, and we have two. We have an inhale counter lung and an exhale counter lung. Ultimately, the gas gets pushed into the center core, and there's a carbon dioxide scrubber. It's a soda lime chemical that absorbs the carbon dioxide, and what comes out of the other side into the breathing bag and back into our mouth is gas that's free of carbon dioxide. The important part though is that oxygen that we exhale is still there. You have two cylinders on the rebreather. You have this one on the diver's right side, that's oxygen, and you have this one on the diver's left side, that's what we call a diluent. It dilutes. Why does it need to be diluted? Because oxygen breathed too deeply is toxic. So a rebreather has what we call a controller, and a controller is essentially very similar if you're a diver, a dive computer that you wear. It handles all the other functions of a dive computer, but it also has oxygen cells that monitor the oxygen concentration in the breathing loop. When the oxygen concentration drops below whatever partial pressure that we set, whatever concentration we set, then there's a solenoid, a computer-fired solenoid, a mechanism that opens and closes the gate to allow oxygen to flow into the loop to bring the percentage back up. We can also do it manually, which is the way we tend to do it, by hitting a button on the side, and we can add oxygen that way. Collectively, that is a rebreather though. The unit, when assembled, is about 70 pounds. We talked about the breathing loop, and that's kind of the core of the rebreather. Other components, we have a wing, and the wing is a device that allows us to add gas to it. We can do it with a power inflation, or we could orally inflate if the power inflation did not work. And that allows us to be neutral. So we talked about this unit being 70 pounds roughly and so on. If we were to roll off of the boat and hop in the water pre-dive with no air in the BC, we're going down, right? So we add gas initially so that we're positively buoyant, floating nice and safely on the surface. When we're ready to descend, we press the button and it will drop gas out, and that allows us to be negative so we can descend in the water column. And when we get to the depth that we want to be, then we're going to add gas back to the BC. It's going to displace water and allow us to be neutral. So that's a buoyancy compensation device. The other component is, we have to wear it, right? We have all this equipment, but it needs to be mounted to our back some way. And that is what happens with this metal back plate. It has a cover on it, but it's actually a stainless steel back plate. And then the stainless steel back plate has a harness, and the harness is what we are physically in, and this is what takes up the weight of the unit when it's on the diver's back, along with a little crotch strap. When you add gas to this wing, as we were talking about, it keeps the unit from floating up on you. So it kind of like mates the equipment to your body. For safety, it's kind of a diver 101. We usually have some type of cutting tool, cutting implement, knife, and dangers for divers tend to revolve around monofilament or fishing line, or something that might entangle the diver. So these tools tend to be relatively small, but something to cut with. And maybe lastly, we have gauges. And the gauges are attached to the regulator, so the diver can see their diluent supply, and in the counter lung on the diver's right side, they can see their oxygen supply. On the mouthpiece, there's also a mouthpiece retaining strap. The genesis of the mouthpiece retaining strap was to prevent drowning if a diver were to lose consciousness. And divers can lose consciousness for certain reasons, but one of them might be a very high oxygen content. And there are all types of ways that we mitigate that, so that this is not something that commonly happens, but it could happen. So recognizing that, primarily military divers came up with this mouthpiece retaining strap, which goes around the neck, you pull it tight, and in the event the diver kind of loses tone because they're relaxed or unconscious, then it keeps the mouthpiece from falling out of the mouth and the diver from aspirating water. And then it has this flange around it, which pushes up against the diver's lips to make a good seal in the event that that were to happen. So that's one reason. And the other reason is it reduces jaw fatigue. You know, training can be 30 minutes, 45 minutes, or an hour. Although, as my team likes to tell me, our training dives can get quite long, maybe like 2 or 3 hours. But our working dives, you know, because of the decompression, because of the depths that we go to, sometimes upwards of 152 meters, 500 feet, those dives could have 4 hours of decompression and could have a surface-to-surface time of anywhere from 5 hours. Maybe our longest dive is about 6 hours to date. That's a long time clenching and holding this in your mouth. So the mouthpiece retaining strap tends to reduce the jaw fatigue and makes it much more comfortable for the diver to stay on the loop for extended periods of time. So next we have what we call a bailout cylinder. We call it a bailout cylinder. It's simply a scuba cylinder though. It's only 40 cubic feet. It's a cylinder with a valve. And then we have a regulator attached to it. The regulator configuration is a little bit different. And I should start with, we use this in the event that the rebreather were to fail. This is all about safety. Seldom do we ever use bailout gas. The regulator is stored on the side. If the person is not a technical diver, then there might be like, well, why is the regulator on this long hose and stored in this way? So this gas is on the diver's side. So we talked about the harness before, and one of the things I failed to mention is that the harness has D-rings. So there's a D-ring here that this would snap to, and there's a D-ring here that the bottom snap would snap to. So essentially the diver is wearing this bailout on their side. If we are doing a deeper dive, a dive where we will require more bailout gas volume-wise because we're deeper, or if we require more or different types of bailout gas because of decompression, then we would carry multiple cylinders. So traditionally we'll carry, one cylinder and another one, so 2 bailout cylinders on our side, and we might carry a third or a fourth clip behind us, which I can't levitate, so I can't really show you on camera, but we can always find some footage. So that's our bailout system. Every rebreather diver carries this. This is like a crux, a core piece of rebreather diver safety, irrespective of depth. The next item is a diver propulsion vehicle. In scuba lingo, we call them scooters. It has 2 core functions. The first is fun. They're very fun, right? Imagine, kicking through the water column versus hitting a trigger and being pulled through the water column at whatever speed you want to be pulled at, almost. It's a lot of fun. But for the depths that we dive to and the distances sometimes we travel, this becomes absolutely necessary when we're diving super deep. So if we think about a typical scuba diver with that standard cylinder on their back and their BC, they don't look that encumbered. They don't look like they're wearing a lot. But we compare that to the rebreather, it's a lot more equipment. A lot more equipment in the water means a lot more drag. So a lot more drag means a lot more effort for us. And carbon dioxide is the thing that we're always trying to eliminate. And we do that by using any type of tool that will help us move less. And a scooter is one of the #1 tools for that. You hit the trigger and it runs. And it doesn't sound like a lot right there, but this will move the diver, somewhere around approximately like 150 feet per minute. So this particular DPV has speed control, and the speed control is in the trigger. So it starts in 3rd gear, it has 8 gears. So if I click twice, it goes up a gear. If I click once, it goes down a gear. So that's 3rd gear, 4th, 5th, 6th, 7th, 8, and that's as fast as it goes. That speed right there, even though it doesn't seem like much here in the dive locker, it would cause an immense amount of pull on the diver's body. As a technical diver, with all the equipment we use, realistically, 3rd gear, and then down the 2nd, and down the 1st, the slowest gear. is what we use 90% of the time. It's the most comfortable, and it also gives us the longest duration on the scooter. If we were on that 8th gear, that ridiculous, ludicrous speed gear, you would probably get something like 15 to 20 minutes. On the lowest gear, you're looking at something like 2.5 to upwards of 3 hours. So it's also much more efficient. For longer travels or longer durations, we find that it's a lot easier to mount a kayak compass. Makes it a lot easier versus trying to scooter and look at a compass on a wrist or on a computer or something. So that's why you see the compass there. Collectively, these pieces of equipment, along with a few others, are what allow us to do our deep research here at the California Academy of Sciences, do it and also do it safely and efficiently.